Chapter 13 covers the basic concepts and applications of chemical equilibrium. I will divide the lecture for this chapter into several parts. In the first video, we'll discuss the concepts of dynamic equilibrium, reaction quotients, and equilibrium constants. Before watching this video, make sure that you have watched the dynamic equilibrium video posted in Canvas and have completed the reading guides for that video and for sections 13.1 and 13.2 from the textbook. Print out the Chapter 13 handouts and have your copy handy to take notes on as we work through the various sections. Chapter 13 starts with a discussion of chemical equilibria. You also watched a video on this topic. The concept of equilibrium is used to describe reversible reactions that don't go to completion. Equilibrium is characterized by the presence of both reactants and products at the end of the reaction. We also show equilibrium by using a double arrow in the reaction equation. The following are some key ideas from the assigned video. In order for chemical equilibrium to be established, the system must be a closed system. At equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. Equilibrium position is also temperature dependent. We say that the system is dynamic because even though it looks like nothing is happening, on the microscopic level, forward and reverse reactions continue to happen. What determines the position of equilibrium? How can we know how much products will be made for a given reaction? Let's start by looking at some reactions we've seen before. Hydrochloric acid is a strong acid, and when it reacts with water, it produces the hydronium ion and chloride ions in solution. When this reaction reaches equilibrium, there is essentially no HCl left because HCl is a strong acid. This reaction lies strongly towards the right or towards products. On the other hand, hydrofluoric acid is a weak acid. When this reaction reaches equilibrium, there is mostly HF in solution and very little hydronium ion or fluoride ion. We say this reaction lies strongly to reactants. Let's look at another example of a chemical equilibrium. The next few slides, the ones with the blue background, come from the reading guides for this chapter. You were asked to view posted images in Canvas from the simulation of the reaction of iron 3 with thiocyanate to form FeSCN2+. In this simulation, you can change the amounts of reactants and products that you start with and let the reaction run until equilibrium is established. We'll look at how the equilibrium amounts of reactants and products change with different starting conditions. Pictures of the simulated results for 5 different trials are posted in Canvas. You were asked to complete the table shown for these 5 runs. In run 1, we started with 0.0050 molar of the Fe3+ ion and 0.007 molar of the thiocyanate ion. The Fe3+ is shown with a red line on the graph, and the thiocyanate ion is shown with a black line. The product, FeSCN2+, is shown with a blue line. As the reaction begins, it is proceeding in the forward direction to convert reactants to products. The concentrations of the reactants thus initially decrease with time, and the concentration of the product increases. After some time, however, the concentrations stop changing and we have reached equilibrium. Notice that at equilibrium, there are some of each of the reactants and the product present. Let's walk through completing the table for the first run. We can enter the initial concentrations of reactants and products. Since there is less Fe3+ than SCN-, iron 3+ is our limiting reactant. If the reaction would go to completion, we would expect to form 0.005 molar of the product FeSCN2+. However, we see that at equilibrium, we have the following amounts of reactants and products present. If we were to calculate the percent yield of the reaction by comparing the equilibrium concentration of the product FeSCN2+ with the stoichiometrically predicted amount, we see that we get a percent yield of 41%. If we complete the table for the next 3 runs, we see that none of the reactions go to completion. In run 2, we started with 0 iron 3+, 0.002 molar of the thiocyanate, and 0.005 molar of the product FeSCN2+. We actually end up at the same equilibrium position as the first run. However, runs 3 and 4 ended up with different amounts of reactants and products at the end, and with different percent yields. Notice that none of these reactions go to completion. Is there any way for us to predict the equilibrium position of the reaction? Let's try calculating the ratio of concentration of the product, FeSCN2+, divided by the concentration of the Fe3+, and the concentration of the thiocyanate ion for each of the runs in the simulation. Interestingly, we see that despite the fact that the runs reach different equilibrium concentration, this ratio is a constant for all the runs. This is a general result. We now return to the Chapter 13 handouts. The general result that we saw on the previous slide is called the law of mass action. And the constant for each reaction is called an equilibrium constant. For a generic chemical reaction of A plus B going to C plus D, the ratio that gives the concentrations of the products raised to the power of their coefficients in the balanced chemical equation divided by the concentrations of the reactants, also raised to the powers of their coefficients in the balanced chemical equation, turns out to be a constant. In our reaction, where we had Fe3+ plus thiocyanate makes FeSCN2+, this ratio of product concentration to reactant concentration is shown. And we saw that this ratio had a constant value at equilibrium. Again, this is a general result that this will give a constant value as long as the temperature is the same. The ratio of the concentrations of the products raised to their coefficients divided by the concentrations of the reactants raised to their coefficients will have a constant value if the system is at equilibrium. That value is called the equilibrium constant and is given the symbol capital K sub C. Notice that we use a capital K for equilibrium constants to distinguish them from the rate constants in Chapter 12, for which we used a lowercase k. The subscript C in these expressions is used to denote the use of concentrations. When the system is not at equilibrium, we can still write this ratio of concentrations, but we give it the symbol Q sub C to denote non-equilibrium conditions. In this case, in the concentrations, the subscript T is used to denote that the reaction is not necessarily at equilibrium. When we compare that to the Kc expression, where these concentrations must be equilibrium concentrations. An important point is that at equilibrium, the value of Qc will be equal to the value of Kc.